we started looking at the auxiliary point method for acceleration analysis. So, if you have two bodies that are connected, and if I know the acceleration of some point A, so let us say this is I, this is J. And I know the acceleration of point A. Okay. I can relate the accelerations of point A and B along a line that joins A and B in this manner. So, I can draw what is called an auxiliary line. And then if this is the component of the acceleration of A along this, then the component of B along this, B is the motion transfer point, is related to this one as this plus omega I square B A. Okay. So, towards A. Okay. So, I can say that these two accelerations are related in this manner. In the case of velocities, we saw that they would be equal, but here again, because of the fact that A and B are points on a rigid body, B can only move along a circular path with respect to A, which means the normal acceleration gets added by this. There is an additional component for the acceleration along that line 1. Then if I take a point C on this auxiliary line, but which is located on body J, I can say that the acceleration of C is this plus omega j square C B. Okay. And then I can substitute for the first one as AAI plus omega I square BA plus omega j square CB. So, I can relate points along the auxiliary line in this manner. Okay. So, now if I know one component of this acceleration, I am interested in finding the acceleration of C, because I know nothing about body J. So, if I know this is one component, then the other component necessarily has to be, the total vector, the head of that vector necessarily has to be along this line that is perpendicular to this component. Okay. So, that means acceleration of C is somewhere such that the arrowhead lies on this line xx. So, now I have narrowed down my where the acceleration of C lies using one component. So, I will need one more component. So, if I know the component along one other direction and I draw the perpendicular to that, wherever these two normals intersect will give me the location for the arrowhead for the acceleration of point C. Okay. So, like that, so then I can determine the acceleration of point C. Similarly, if I can find one more point that is also located on body J, then I can find, and if I can find the acceleration of that point, the acceleration of body j is completely determined. So, this method for acceleration analysis is applicable to mechanisms of low and high degree of complexity, kinematic complexity. Because all the omegas, the normal component only depends on omega, which is known, completely known once you have done the velocity analysis. Most mechanisms that you encounter can be solved with this. Okay, I should say DOC. DOC is so here once if AAI is known, then the line XX on which knowing a component along another auxiliary line we can find the acceleration AC by finding and another normal YY to the other component. Okay. So, the auxiliary lines are drawn through the, I will come back to it. Through the motion transfer points along directions in which components of can be determined. So, they may be known either because alpha is known, either because of the input that is given to the mechanism, or they may be known because they are normal components which are determined after the velocity analysis. Okay, so, those are the two cases where you would know the, and the auxiliary points which are considered as points on the floating link of two auxiliary lines, and you only need two such points. are sufficient to completely determine the acceleration of the floating link, angular acceleration or acceleration of any other point on the floating link. Okay. Let us do an example. Yes.
So here it gives you a complete acceleration of that point, right?
Yes.
So how do you know what, say, the angular acceleration?
This is, you need 2 points, that is why.
No, but
This is here you only know, right now I do not know the full acceleration of this point, see.
so once you have the other point, you have the complete, the vector.
Yeah.
So then that, like,
That gives me the acceleration of point C. That is not enough to give me the angular acceleration of the link. I need the acceleration of one more point to know the angular acceleration of the link. So, the question was, is that sufficient to find the angular acceleration of the link? Acceleration of one point is not sufficient to find the angular acceleration of the link. That is why typically you need 2 auxiliary points. Not typically, you always need 2 auxiliary points, unless you know the angular acceleration by some other means. Okay. See, rigid body, 3 degrees of freedom, right. So, the acceleration gives you 2 linear for the, you also need to know the angular acceleration. So, it is 3 quantities, but if here, because we are finding accelerations of points, you need one more point to find the acceleration, angular acceleration of the body. If you are into, so you have to know omega before you get into acceleration analysis. You cannot venture into acceleration analysis without doing velocity analysis. You cannot venture into velocity analysis without doing position analysis, because you need all the thetas. So, they have to necessarily follow that order: position, then velocity, then acceleration. This whole thing hinges on the fact that we know the omegas, right. So, which you may have again found out using the auxiliary point method, but there of course it was simpler because the velocity is directly transmitted between 2 points in the rigid body. So, let us do an example. How many degrees of freedom for this mechanism? Only 1. Okay. But if this is my, so I am given that my input is omega equal to 10 radians per second and it is constant. That is the input I am given. Let us assume the velocity analysis has been done. Okay, so you know all the omegas. So, let us say 1, 2, 3, 4, 5, 6. For the velocity analysis also you probably have to do, you have to use the auxiliary point method, because you can't use the velocity difference method. And similarly for the acceleration analysis also, because I do not know how the path of this point, let me call it A, B, C, D, this is O, D, okay. Let us say this is O, C. Okay. I do not know the path curvature for the point B. So, I cannot write velocity of B equal to velocity of A plus velocity. I can write it, but I can't solve it. So, I could write that still holds, the relationship still holds, okay, or acceleration, assuming we have finished the velocity analysis. This still holds. However, I do not know anything about the acceleration of B because I do not know the path curvature. I do not know for B relative to A, okay, I do not know what. So, I do not in this one I will have, I do not know anything about the magnitude or direction of the this one and about this one either. Okay. So, I can't solve this, I have more than one unknown. So, I have to go to some other method, I can't use the acceleration difference method. So, let us try the auxiliary point method. Okay. So, what are the things that I know here? So, I know omega 2 is constant, therefore, my input alpha 2 equal to 0. I am given one acceleration input, alpha 2 equal to 0. Now, so I know the acceleration of A completely. What is that going to be equal to? Yeah, so it is just going to be omega 2 is given and it is given that it is constant. Okay. So, I know that the acceleration of A is just this. This is the full acceleration of A. Okay. Now, BCD is my floating link. Okay. And I want to find, I actually want to find the accelerations of everything else in the mechanism. But the problem is because BCD is a floating link, this is a mechanism with complexity. Is it a high degree of complexity or low degree of complexity? Are you sure? What's a low degree of complexity?
If I can invert it and solve, then it is a low.
Yeah. So, in this case, okay, acceleration is not so simple to do by inversion, but velocity at least I could do by inversion here. If I had 6 or 5 as my input, then I can easily find, so velocity analysis I can, so as far as that is concerned, it is a low degree of complexity. Kinematic complexity wise, it is a low degree of complexity because if I had 5 or 6 as the input, then this is not really a complex mechanism.
Can we also solve this in the similar manner by taking an acceleration for 5 and then the
There is a way to do that, there are, but it is not directly, you cannot directly scale. Again, you know, there are methods called method of normal components, there are methods like that where you give it a 0 angular acceleration, okay, and then solve for all the normal components will not change because the normal components depend only on the angular velocities. So, they will not change when the angular acceleration, whether it is present or not. So, there is a way you can solve, you find the components of the normal which will not change, and because of that then you can go back, put the actual angular acceleration and solve for it. There is a method like that, because I do not want to go into too many graphical methods, I am not doing it, because that will also fail with some mechanisms. The auxiliary point method is the one that can be used with most of them. So, that is the reason I am doing this one and not there is that is called, I think, Goodman's indirect method. If you want to look it up, I can post some information on that. Okay. So, you can do that, but it is a lot more complex in terms of the graphical analysis. You have to do the analysis twice, once with 0 angular acceleration and then use those normal components for the acceleration and then solve with the actual angular acceleration. But yes, it is possible to do that. So, this is actually a mechanism of low degree of complexity which can be solved by that method, because if I change the inputs to 5 or 6, then it is possible to do that. I think that is called the method of normal accelerations. There is also a Goodman's indirect method, maybe, but they all, the basic principle is the same. The normal components of acceleration are dependent only on the angular velocities and do not change because of the angular acceleration. Okay. So, here I know the acceleration of A. Okay. So, I want to find the first, let us say, acceleration of the ternary floating link BCD, okay, because if I find that, then I can basically find the other things also. Okay. That's the problem element there. So, how would I choose my, so the motion transfer points for this link are B, C, D. The motion transfer points to the ternary link are B, C and D. Okay, those are the motion transfer. That is where it is connected to the other links. Now, I can choose my, so what do I know? So, if I look at point B, okay, I know the acceleration of point A. Okay. So, I could take an auxiliary line along this. That could be one auxiliary line. Okay. What are the possibilities for other auxiliary lines? OCC, I know the normal component of acceleration of C. So, I do not even have to know the full acceleration of the point C, of the motion transfer point. I know the normal component, okay, I can use that. So, since I know one component, I will take another auxiliary line through that. So, I take another auxiliary line through that, and then I could take similarly with ODD, because it is again D is a point on a link that is rotating about a fixed pivot. I know that D has a normal component of acceleration along ODD. So, I take my third auxiliary line along that. Okay. So, now I have 3 auxiliary points. I call this X, Y, Z. I only need 2. I don't need all 3. Okay. So, I only need 2. The important thing to remember is X, Y and Z are considered points on which link? Points on link 4. Okay. So, you have to imagine that link 4 encompasses all this. Okay. So, they lie on link 4. So, now I will apply the, so I know A completely. So, I know the component I can find the component of A along this. So, this component here is AA along 1, that is known. Okay. So, I can use that to find AB, 1 is nothing but AA along 1 plus omega 3 square into BA. Okay, omega 3, because B and A lie on link 3. AX, motion is transferred to X, which is on link 4, that is equal to AB plus omega 4 square XB. Yes. So, I can write it in one shot. I can look at it as long as I make sure that I get the correct omegas. I could write this in one shot as AX along 1 is AA along 1 plus omega 3 square BA plus omega 4 square XB. So, I know that component, completely known, because my velocity analysis is complete. So, I know that this component here is AX along 1. Okay. Now, I need one more component for the acceleration of x. So, I know that the acceleration vector of x lies somewhere on this perpendicular to this component. Okay. I need one more component for the acceleration of x. So, look at another auxiliary line. Let us say we take this one 3. Okay. So, this is along, I can write acceleration of x along this auxiliary line 3 is what would it be? Acceleration of d along 3 plus omega 4 square xt. Yes, what is this acceleration? This would be omega 6 square into d OD. That would be acceleration of d along 3. Towards OD, you would have that acceleration, normal component of acceleration, plus omega 4 square xt. Yes. So, now I know one more component, which is say this is A x the direction 3. So, now if I construct a normal to this where it intersects this, I know my acceleration of x is this. Okay. So, acceleration of x can be split into either these two perpendicular components or these two perpendicular components. So, I found the acceleration of one point on the floating link. take point y or point z. Let us take point z. Okay, so this is for x. Similarly, now I can write I know along 2 the acceleration of z along the line 2 will be equal to acceleration of c plus omega 4 square. I do not need to consider y because y is just an intermediate point. I can 2 points have to be on the floating leg. So, acceleration of c plus omega 4 square c. Okay. That gives me one component. Acceleration of z, the other auxiliary line passing through z is 1, is acceleration of a plus, I have to consider b because b is a point on common to, because omega 3 will be different. Okay. So, acceleration of a along I plus omega 3 square b a plus omega 4 square z b. Okay. So, I will get a component along this, component along that, fully known. Then I construct normals to these two components so this I can call, for instance, I can call this x dash, the point where the head of acceleration of x lies. So, I can construct normals to these two components to find which point, c dash, which will give me the acceleration of point z. Now, y and z are points on the same link, link 4. Sorry, x, right, x and z are both points on link 4. I have found acceleration of z. Okay. So, if I write, I can now relate these two accelerations like this. Completely known, completely known. Only unknown is alpha 4. So, if I know the normal component of this, from the tangential component, I can solve for alpha 4, which is the angular acceleration of that link. I can then easily find the acceleration of D, acceleration of B, or the acceleration of C, because I can just use image. I can construct this figure in the acceleration diagram such that it is similar to the figure in the position diagram. Okay, so I can get the absolute accelerations of, or I can use the equation, acceleration of x is acceleration of b with respect to x or to z, and I can find, because I know alpha 4 now. So I can find the values of, I can find the vectors, and once I do that, then it is easy for me to determine what is alpha 6, alpha 3, alpha 5. Straightforward. Once I know, acceleration of B, acceleration of D, acceleration of C, okay. From that, alpha 3, alpha 5, alpha 6. Okay. Any questions? Is that clear? What if you want to find for multiple positions? This may not be the graphical method may not be the best way to do it. So, let us go back to, I made a mistake here, which the direction of, if you look at AX along 3, okay, AX along 3, this should be towards OD, okay. So, when I had drawn it the other way, so I guess this should be AX along 3, that should be the direction, in which case again this is also wrong. So, I have one perpendicular like this, the other normal is like this. So, this will be the point x dash, and this will be the acceleration of point x, okay. Just a, so AX along 1 is towards A and AX along 3 is towards OD, okay. I had it drawn in the opposite direction, okay. So, this is the corrected acceleration of x. So, let us see how we can, whether we can do these sort of mechanisms analytically as well. Okay. So, my vectors so I have one loop. So let's call this R1, R2, R3, R4, R5. So one loop formed by R1 through R5, the other loop formed by R6. So the other loop is R1 dash plus R6. So let's write out the two loops. I have one loop R1 dash plus R6 equals R2 plus R3 R4 dash. Okay. The other loop is R2 plus R3 plus R4 equals R1 plus R5. Excuse me. Okay. Two loops in this mechanism as it. So let me directly write the velocity equations. So if I differentiate one, I will get R1 dash will not be there, does not change. So I omega 6 R6 e power I theta 6 equals I omega 2 R2 e power I theta 2 I, what will it be, omega 4 R4 dash e power I theta 4 plus some constant gamma, because that angle does not change. And for the second loop I have I acceleration is, for each one of these I will have I will write it in vector form, minus omega 2, sorry, I omega 6 alpha 6 minus omega 6 square R6, I am writing it back in vector form, R3 plus I alpha 4 minus omega 4 square R4 dash. And for the second equation I have I alpha 2 minus omega 2 square R2 plus R5. Okay. So how many equations do I have? For the acceleration? 4 equations. How many unknowns do I have? What are the unknowns? 4 unknowns, alpha 3, alpha 4, alpha 5 and alpha 6. Alpha 2 is input. That is what I gave you, no, in the previous same problem as earlier. Alpha 2 is input equal to 0 in this case, because omega 2 is constant. So, I can set up the matrix and it is all linear equations. Once my position analysis is done, velocity analysis is linear, so is the acceleration analysis. So, I can just solve this for alpha 2, alpha 3, alpha 4 and alpha 3 to alpha 6. Okay. So, I could solve, if I have to do it for several points, this is probably the way to go. So, the analytical method also will work, because you are basically just solving a set of simultaneous equations. Even though the acceleration difference, those methods do not work, this will work, so will the auxiliary point method.